We've come to the last chapter in this unit, angular momentum. As we did near the end of the last chapter, we won't derive angular momentum from linear momentum. We're just going to substitute in the angular values for the linear or translational ones. So linear momentum is mass times velocity. So we're just going to take the angular equivalents and we will call angular momentum is I omega. Not sure where the L came from. Maybe they took the L out of angular. I don't know. But in any case, L, angular momentum, is equal to I times omega. A very quick review of linear momentum. The conservation of linear momentum states that in the absence of external forces, momentum is conserved. This is a direct consequence of Newton's second law. And this again is how he portrayed it in Principia. The sum of the forces is the change in momentum over the change in time. If you have no external forces, if the sum here is 0, then the change in momentum over the change in time equals 0. That means the change in momentum is equal to 0. And when a quantity doesn't change, we call it conserved. So this is the conservation of linear momentum. Let's take the rotational version of Newton's second law. Instead of sum of the forces, we have sum of the torques. And instead of linear momentum, we have angular momentum. And time, of course, is the same in both cases. If there are no external torques, the sum of the torques is equal to 0. Then that means the change in angular momentum is 0. There's no change, so angular momentum is conserved in the absence of an external torque. The standard example used to illustrate the conservation of angular momentum is the ice skater. Also, a lot of labs have a little seat with a wheel on top of it that you can sit on and rotate, and then that's also a good way to do this if you don't have an ice skating rink in your classroom. Start by assuming a frictionless surface. Ice is pretty close to that, although in reality, if it were totally frictionless, the skater would not be able to stand up and skate, and none of this would work. But friction is pretty small. The skater starts with his arms stretched out and starts spinning in place. He then pulls in his arms. What happens to his rotational, his angular velocity, after he pulls in his arms? Discuss this in your groups for a second, and then click on the below link and see if you were correct. Why did this happen? The nearly frictionless surface assumption implied that there is no net external torque on the skater, so the conservation of angular momentum can be used. So here's Newton's law, second law. Sum of the torques is 0. That means that the change in angular momentum is 0. Which means your initial angular momentum is equal to your final angular momentum. We make the substitution that angular momentum is moment of inertia times angular velocity, and then we solve here for your final angular velocity. Now, the human body is not a rigid sphere or a hoop or anything simple. But going back to what the definition of moment of inertia is, at what point in the spinning, whether the skater has his arms out far away or pulls them in tight, at what point does the skater have a greater moment of inertia? When the skater's arms are stretched out, more of his mass is located further from his axis of rotation. The skate's on the ice. So let's draw a picture of that. We like drawing sketches here. So here's the skater. And his legs are close together because he's spinning around, and here's his arms out here. So a bunch of his mass is further away from his axis of rotation. When he brings his arms in, this should be the same guy, although he looks a little taller. Here's his arms close to his body. The moment of inertia here is going to be less than it was over here. More of his mass is closer to the axis of rotation. So in the video you just saw, his initial moment of inertia is greater than his final. So this I0 is greater than IF. So when omega F is greater than omega 0, the skater will rotate faster with his arms tucked in. His final angular velocity will be greater than his initial angular velocity because the change in moment of inertia of the skater.